So good morning, everybody. My name is Paolo Di Lorenzo from CNIT, and today it's my pleasure to give this presentation on the role of RIS in enhanced communication networks on behalf of the work package 4 team. Now, essentially, this presentation is a brief summary of all the work that we have been doing within Work Package 4. I will start from the objectives of our RIS enhanced system, showing then very briefly network architecture and deployment strategies that we have considered. And then I will go through fundamentals and design of multi-user techniques for both RIS enhanced communications and mobile edge computing. So the main question that we have considered here is how to design and optimize an RIS enhanced system for enhanced connectivity in considering both legacy frequencies and also higher frequency bands. What we have been targeting is actually boosted connectivity, enhanced coverage. We wanted to improve spatial multiplexing capabilities, reducing outage probability, enhancing the capability of mobile edge computing thanks to the presence of multiple RIS, and also control and monitor EMF radiation. Now, as we will see, the solution has to be that we have found need to be tailored to the different RIS hardware that we have at hand. For instance, we might have only reflective, so fully passive architecture, or hybrid, as George was showing in his presentation, where we have some active elements that can perform more sophisticated operation, or controlled versus autonomous, where in the first case we have an external entity that controls the RIS, or in the second case we have an autonomous RIS that have to set up by itself. Now, regarding network architecture and deployments, we have considered mainly 3 scenarios. The first one is boosted and a railway station. Here, for instance, we can see that without the presence of RIS, we have several coverage holes that putting, let's say, on this scenario, some, let's say, RIS, which are these red dots, we can see a large improvements in terms of SNR and coverage. We have also another scenario which consider nomadic RIS, where actually the RIS are put on top of a UAV to perform on-demand, let's say, services in terms of extended coverage whenever it's needed. And in this case, of course, trajectory and beamforming needs to be optimized jointly due to the, let's say, fluctuation of the movements of the UAV. And finally, we have considered edge computing, because since in this case, blocking effects can severely hinder the performance of MEC due to poor offloading rates and consequent underexploitation of the edge resources, and thus the performance of RIS can, let's say, boost MEC in this case. And then we also consider, let's say, 2 different control channel strategies. The first one is explicit. In the case, essentially, we have an external entity that takes, for instance, the CSI information, process the data, and sends the configuration back to the RIS controller, or implicit, where actually local CSI is used to, let's say, self-optimize the RIS configuration. Now, regarding the fundamentals of multi-user, let's say, connectivity, the first aspect that we have considered is the active and passive beamforming optimization. So there was this nice work from NEC, RISMA, RIS-aided multi-user alternative optimization, which consider a downlink scenario where actually it's done a joint optimization of the beamforming strategy at the base station and the RIS parameters to provide, let's say, high bandwidth, high capacity communication. And there is also another strategy which consider quantized RIS optimization, where actually 1 bit phase shift is optimized using quantum annealing strategies, searching actually of the Ising and Miltonian of the spin array that maps the RIS. Of course, all the details can be found in the papers that you can find below. Then we have also this exploitation of the frequency domain. We have this actually novel design that's actually enabled to operate over different radio frequency maps without the need of changing the RIS hardware. And is also this novel concept of RIS that acts as a frequency mixer, and this particular simplifies a lot the channel estimation procedure, which is typically very, let's say, complex in this kind of systems. Then regarding the design of multi-user techniques, as a first step, we considered the access. So we, in the context of massive random access, the first technique that we have considered is a beam sweeping through a finite set of RIS configuration, and a channel oracle procedure that enable the access from massive users with the aim of maximizing the throughput of the system. Then we move to practical channel estimation techniques. Also here we have several works. For instance, the first one that exploits slow changes in the channel, in the cascade channel, actually in the RIS base station channel, enables an estimation that is both reliable and fast of the cascade channel, exploiting and hinging on a tensor-based modeling, which is then solved using, let's say, very reliable algorithms such as alternating squares and so on. And then having the possibility to have hybrid RIS, it's also possible to estimate the individual channels, so the base station RIS channel and the RIS UE channel, rather than the cascade channel, as shown in this paper number 4. Then we move to the RIS optimization in practical environments. The first contribution actually considers some rate optimization of the system based on statistical position information, and it alternates between two optimization phases, a long-term phase for the RIS and a short-term phase for the base station. And here, essentially, all the information of the user position is known in the statistical sense, and this can be either known a priori or learned over time through some learning mechanism. And then in the case of autonomous RIS, we have also RIS orchestration algorithms based on reinforcement learning, where the RIS controller is modeled as a learning agent that takes actions. For instance, an RIS profile and the MIMO precoding matrix, and the environment then reacts, for instance, with some signal-to-noise ratios at the users, and then the controller keeps learning over time, adapting to the time-varying channels that it observes. Finally, we have applied RIS to enhance the capabilities of mobile edge computing. In this case, we have several devices that want to offload computation to an edge server that runs sophisticated applications on the user's behalf. In this case, what we have done, we have proposed a joint optimization of communication and computation resources jointly with the parameters, the phase shift parameters of the RIS, in order to minimize the overall energy consumption of the mobile edge computing system, subject to long-term constraints on the average end-to-end delay. And we have shown that in this case, RIS can boost a lot the performance of MEC, especially in the presence of intermittent channel given by, for instance, millimeter wave communications. Finally, we have also applied RIS in the context of federated learning, which is a particular case of goal-oriented communications, where the goal is actually to train a common machine learning model of interest, for instance, a neural network. And we have shown that also in this, let's say, goal-oriented scenario, the RIS can be highly beneficial in improving the trade-off between energy, latency, and accuracy of the goal-oriented communication system. So to summarize, to conclude, actually during the project in VUP4, we have investigated several architectures, considering also control strategies and deployment strategies. And we have devised both fundamental methods, but also practical techniques for multi-user RIS-empowered communications, encompassing and mobile edge computing, encompassing all the aspects. So access, channel estimations, control, resource optimization, taking also into consideration computation aspects in the mobile edge computing cases. And in all the practical scenarios that we have considered, we have been able to show large performance improvements. So with this, I conclude my talk, and I thank all of you for your attention.